call that a distance 1. And how far does the fulcrum point have to be from mass 2? We'll call that a distance 2. So that's our setup so far. Well, we want to use this setup to extend all the way to where would you visualize this as a three-dimensional object under this, say, strange-looking table. Any questions so far with the setup of our problem? Okay, then it's been verified through many, many repeated experiments that the location of this fulcrum where the whole system balances will satisfy this equation, that mass 1 times distance 1 must be equal to mass 2 times distance 2. So that's our fundamental idea to work with. And if that's all we had, then we would be kind of stuck because we're trying to go to a case where we have both an x-axis and a y-axis. So we need to impose something extra to the picture, an entire x-axis. So let's just throw that on there. So we have an x-axis in the picture. The origin could be, say, at the fulcrum. It could be anywhere convenient. We don't necessarily have to throw an origin on our picture. But if you like, if it hurts you not to have an origin on your x-axis, we could just throw it out there, and that'd be fine. So with this setup, we could say that now that we're looking at an x1, or an x-axis, we could think of this as being at point x1, poor red chalk. This being at point x2, and we'll call this point where the fulcrum should rest x bar. So that's our setup now after imposing an x-axis to the system. So if we work with that equation, mass 1 times distance 1, we now have things we can put in there, and we can in fact solve for x bar next. Any questions first to that step so far? Okay, so let's work with this equation here. So mass 1, there's not much to do with it. It just is what it is. But we can find an equation for distance 1, this segment. This point is at x bar, so distance 1 should be x bar minus that value there where the mass 1 rested, x1. So that must be equal to, similarly, a mass 2 from this formula times a distance 2, where distance 2 should be x2 minus x bar. So we have x2 minus x bar. So in this diagram, this is something we can set up, get an equation from which we can solve for x bar finally. So let's do that now. Just a spot of algebra, we can distribute, get m1 x bar minus m1 times x1 equals mass 2 times x2 minus mass 2 times x bar. So if we say add m2 x bar to both sides of the equation, we'll have mass 1 x bar plus mass 2 x bar. Let's also add mass 1 times x1 to both sides of the equation to get m1 x1 plus m2 x2. Okay, so far we're on the right track. We can factor x bar out, multiply it by mass 1 plus mass 2. Then that would be set equal to mass 1 times x1 plus mass 2 times x2. And we're just a division away. So if we impose an x-axis, if we have coordinates for x1, x bar, and x2, then we can say the actual value for x bar should be mass 1 times x1 plus mass 2 times x2 divided by mass 1 plus mass 2. So there it is. That's the solution of our one-dimensional case problem. No calculus has happened so far, but we're eventually going to extend this. Questions first so far? Oh, thank you. Mass 2, x2. Good eye. Other questions or comments so far? Okay, next thing we're going to do is, let's rename some of these things. Let's call x bar equal to a capital M. M is going to stand for moment. We'll define it in just a moment. And lowercase m. Lowercase m will stand for total mass in this system. So let's define those two terms next. Since these will be terms we'll use in the two-dimensional case, and in this case up here as well. So in order to find centers of mass, or centroids, really it's all about those moments. So we say that m is the moment of the system about the x-axis. And we define m to be the summation as I goes from 1 to n. Well, there could be many, many point masses. We did the problem with just 2 point masses, m1 and m2, but there could be, say, 30 of them. The algebra will proceed the same, it's just going to be horrendous, so we skip that. And we're going to say, if we did do that, the numerator would have came to summation as I goes from 1 to n of mass I times xi. And that would be called the moment of the system about the x-axis. If we had another axis, we would have called this m sub y and called it the moment of the system about the y-axis. What it will do is measure the tendency of the system to rotate about the new axis, the y-axis, which is very strange. We're grabbing coordinates off the x-axis, but measuring rotation about the y-axis. But so far, that's our moment, and little m is the total mass of the system. And the equation for total mass is the summation as I goes from 1 to n of mi. So just add up all the masses and you'll have total mass. So that's our setup so far. And in a neat way, these equations maintain roughly their same exact form. We can extend all of our work to finding the center of mass of the region R above. So that's where we're heading for. Any questions with what we've got so far? Okay, so the major point of this problem was to define the working terms, moments and total mass, and the formulas that we use for an x-coordinate for a center of mass in this case. And what we're going to do next is extend it to 2 dimensions. If you folks would like, we could do an example for this problem before we move on. Does that sound all right to folks? Okay, they're really short and sweet examples. There's no calculus, but it's more about reinforcing the calculus and reinforcing how we extend this next to 2 dimensions. So let's just try a quick, short, fun example. So we can say for example number 1, we have point masses located at let's say located on the x-axis at locations x1 is -3, x2 is equal to 1, and x3 is equal to 7. The corresponding masses are m1 is equal to 5, m2 is equal to 4, and finally m3 is equal to 8. And by corresponding, we mean if we have a point mass m2 is equal to 4, say kilograms if you'd like a unit. These are non-unit problems in the book. It must have been a location x2, 1 unit to the right. So that's our setup. What's really great about these problems is if we're doing a problem like this, or if we're doing it in 2 dimensions, or if we're doing the calculus version in the continuous case, you can almost perfectly eyeball the answer and tell immediately if it makes sense. So a really great idea in these problems in the whole of chapter 8 is draw a picture. If that picture involves plotting a complicated curve, that plot would be provided on the actual exam. So you have some reference of what's going on. So my picture, I'll throw the origin 0 here, call this -3, and have a mass at x1 -3 of 5. I'll denote it with just an arrow so I can tell which is the coordinate, which is the mass. Or if you put kilograms there for units, that would do the job as well. So that's 3, let's say 5 is about here, and I'll say that this has a mass of 5. And let's say that 8, even though this is not quite perfect, let's put it here, and that had a mass of 7. So if that was the case, what would you folks say the x-bar location should be? So now, say 3 children on a teeter-totter, where should it balance, in other words? We have small child, large child. This large child has tremendous leverage. Would you put x-bar, say, to the left or to the right of 5? So I'm saying to the left. Folks agree? So maybe slightly to the left. How do you folks feel about that location for X bar? Somewhere right around there. Possibly. Keep in mind my units are not perfect, or my scale is not perfect. I call that 3, so that's 3, so roughly 5. Also, the masses have lots of influence on the problem. We have suddenly a high mass here. But if we want to calculate this, first we'll calculate M. This will be the tendency of the system to rotate really about a hidden y-axis in the problem, which we're going to extend to shortly. So M is going to be mass I times xi by formula. So we take the corresponding mass of 5, multiply by the x-coordinate of -3, and then proceed down the line by that summation formula. So next we go plus, that 0 there is almost a distraction. We go to mass of 5 multiplied by coordinate 5, plus a mass of 7, multiplying a coordinate 8. And that would be the moment of rotation about the x-axis. Yeah.
Yeah.
Oh, sorry.
The plot's kind of messed up.
I think some of your corresponding numbers on the.
Oh,
drawing.
so -3. Oh, that was a 1, wasn't it? Darn it. So I put a mass of 5 way in the wrong place. So 1 here, mass of 5. Thanks. So it goes -3, 1, 7, then 5, 4. I'm not sure where I was looking. Glad I wrote those down. 5, 4, 8. Jeez, that was horrible. Thanks for fixing that, folks. So 5, 4, 8 for masses, -3, 1, 7 for the locations, and I still feel like possibly that was a bad choice for X bar. Let's run with that still. But that means our mass here should have been 5, -3, 4 and 1, 8 and 8.
Actually, it's another 7.
Oh,
On the
geez.
bottom one, on the X.
7 there. Forgot to correct that one. 8 and 7. I was just jumping lists randomly. Thanks for fixing that, folks. So finally, multiply all that out. We have -15 plus 4 plus 56. So that looks like 60 minus 15 for a nice 45 after all the corrections. Does that look better so far, folks? Okay, your participation is valued. Let's now do the total mass equation. Total mass, lowercase m, is the sum of the masses. You have to look at the right location, 5, 4, 8, 5, 4, 8. So 5 plus 4 plus 8 is 9 plus 8, or a 17. So that's our total mass of the system. So finally, by definition, the x-coordinate for the center of mass, or the x value for the fulcrum, will be capital N, the moment of the system, divided by the total mass of 17. So that's the value we would have. If it was 45/15, that would be 3. So we're slightly below 3, whatever that comes out to. Looks like it comes out to, I did not do the problem, it comes out to something. So if it's slightly more than 3, seems like it's slightly below 3, maybe a little bit to the left, about there. That wasn't too bad for a guess for a system where the masses were in the wrong spots. How do folks feel about that problem so far? Okay, so the way we're going to extend this is we're going to call, in the two-dimensional case, this m sub y and this m sub y, and all we need in the two-dimensional case is m sub x and a y bar. Once we have that, we'll be able to extend even farther. Any questions so far with this setup? Okay, we're off to the two-dimensional case next. So this is what we're looking at so far. So in the two-dimensional case, we'll have the x-axis and the y-axis to consider at the same time. We're going to have possibly several point masses. Let's just put, say, 3 in random positions on the board. So this will have coordinates x1, y1. Let's put maybe a point mass here of x2, y2, and maybe a third point mass way out here at x3, y3. So we like to consider this as being an entire rigid system. Maybe it's some kind of steel rods connecting everything, keeping the distances uniform. But we still want to imagine that all of the mass that matters is exactly at these three locations. So the mass that unifies this as a rigid system will be negligible once again in this process. So we'll have at this location a mass 1, a mass 2, and a mass 3. We still want to imagine that there's going to be a fulcrum, but now we have to visualize it as a point under the system entirely. So imagine we're building a table and we're trying to balance it. And if this is some kind of particle board that's very cheap and very, very light, the relevant masses are here and here, we'd like to know at what point under this structure of uniform thickness, uniform density, will the thing balance. You might guess the center of the rectangle or triangle, right? However, that depends on the masses. If this is very, very massive, then the center mass is drawn to it. If these increase in mass, say at different rates, then the point has to adjust as well. So we'll call that point center of mass x bar or y bar, and with where we placed it, this mass must be substantial to have drawn the center of mass to that location. So that's what we're trying to do so far. We can use the same ideas as before and derive this from first principles, but we can also just extend on what we've done so far and define the following. We'll say that m sub y is the moment of the system about the y-axis. It's going to measure the tendency of this whole system to rotate about the y-axis. So by rotating about the y-axis, you can imagine the table just falling over and rotating that way. Or if M1 is massive enough, maybe it falls over this way. And the way it's defined is highly counterintuitive sometimes. It's a summation as I goes from 1 to n. We take a mass I and we multiply it, I would think, by a corresponding second coordinate, say y sub I, but it's in fact the first coordinate, x sub I. So we're doing exactly this process over here. In fact, when we define the moment of the system about the y-axis, we're really defining, about the x-axis, we're really defining this right here. We want to measure how this rotates about the y-axis itself. Does that make sense so far? In other words, we're just imagining we're throwing in a new y-axis to this, and the meaning of m sub y is now the same. Similarly, we can define m sub x. This is the new thing. M sub x is the moment of the system about the x-axis. It will measure rotation going this way, about the x-axis itself. Its definition is m sub y, or excuse me, m sub x this time, the new thing. Summation as I goes from 1 to n, it go up to 3 in this case. We take a mass I, same as before, so the same exact quantities. We multiply by the second coordinates, y sub I, and then that would be our definition. So one way to memorize this is, things are somewhat backwards as a formula from what my expectations would be. So m sub y involves the first coordinates, m sub x involves the opposite coordinates, the second ones. But if you think of it in terms of the tendency of the system to rotate about either the y-axis or the x-axis, then you're spot on for the meaning of those subscripts, even though they do kind of feel backwards. Questions so far? Okay, the last part of the formula we need is lowercase m. Then we can define the center of mass. But lowercase m is just the same as before. It's the total mass in our system, except for the negligible bits that we're ignoring. And its summation as I goes from 1 to n of mi. So with those three components in place, we're ready to define the center of mass in this discrete case, two-dimensional point masses. So we can say the center of mass is x bar, y bar. We have to give both coordinates. The x coordinate itself will be, again, m sub y. It feels backwards because of the physical interpretation. Divide by the total mass. So it's exactly what we did over here. And the new coordinate is m sub x divided by m. So that's our new formula. Let's throw it in for center of mass. Then our idea is going to be to extend this to the continuous case, where the point masses start to have uniform mass throughout. So we ignore the point mass, imagine uniform density in that plate. But we're extending to it, and this is where we're at so far. Any questions to this point? Okay, one thing to note is that the formulas for x bar and y bar in the continuous case are exactly the same. All we have to do is, when we go to the continuous case, give a notion of what my should really be and what mx should really be, and the same kind of process we've done in problem 1 and the next problem is pretty similar. So let's try a two-dimensional problem next. Any questions first before we give it a try? Okay, so let's carefully plot a new system and their point masses and find their center of mass. So we'll start this problem just with a diagram this time. And in this diagram, we have point masses at locations -4, 2, so at -4, 2, there is a point mass of 5. Next location is 0, 5. So here, and the point mass at 0, 5 is 4 this time. Carefully writing these down. Next at location 3, 2, we have a new point mass at value 3. And final point mass is at 1, -2. Where we have a point mass of exactly 6. So that's our setup in this problem. Then once again, if you like, you could visualize this as really being some kind of structure that looks about like, say, this. Everything on the inside, including the beams that connect those point masses, are of negligible mass. So we're going to just analyze the system as if these are the only values that matter. But eventually we're going to do the right thing and consider the continuous case above. So that's a setup. Any questions so far? Okay, then to get to the problem, really this is the whole recipe. Let's do lowercase m because that's the easiest part. Total mass. So lowercase m is adding up these point masses, 5 plus 4 plus 3 plus 6. So that comes out to a total mass of 18 units. Now we need to look at the moments. So we could do m sub y, m sub x. M sub y, by formula, says we'll do just what we did before. We'll take the masses multiplied by first coordinates only. And that's what this is indicating here. The mass I times corresponding coordinate x sub I. So we'll take 5 times -4 for a -20, 4 times 0 for a 0 contribution on that one. It is what it is, but remember this is rotation about the y-axis. So if you put mass on the y-axis itself, no contribution to that rotation. Then plus 3 by 3, so 9, plus 6 times 1 for a 6. So it looks like 15 minus 20 for a -5. So we have one moment of -5. It'll eventually be divided by 18. Questions so far? Okay, let's do the other moment. And this is the new one, m sub x. We'll measure how likely this structure can rotate about the x-axis, whether it falls over this way or if it falls over that way, for example. But now we're just doing really the same thing where the focus is now second coordinates. It's really the same type of formula where we throw in the second coordinates next. So we can visualize 5 times 2, then 4 by 5, then finally 3 by 2, and finally 6 by -2. And that would be, if everything is multiplied correctly in the corresponding way, m sub x. So this works out to, let's see here, 30 plus 6 is 36, minus 12 should be something like 24. Is that all right so far to folks? At this stage, the problem is essentially over, but you should summarize by actually stating what the center of mass is. So I write as the last part of this problem, that x bar y bar is equal to, we take this value here for x bar. Again, it's highly counterintuitive. We take m sub y for x bar, -5, divide by the total mass of 18. Then we just do it again. For y bar, we take m sub x, which is 24, divide by 18. Then, I guess these do reduce a little bit. We have -5/18, then 4/3 altogether. What I would do as a last part of a problem like this is maybe put all that into the calculator. Let me see if I've done that. I have not. But let's say 5/18, well, that's really close to -1/3, right? It's not quite. This is 1 1/3, so -1/3, 1 1/3 is about here. This is where the center of mass x bar, y bar should be. Does that feel about right, eyeballing it? It's pulled pretty low, but remember there is a point mass of 6, so that's a heavy contribution there. And it feels like it's somewhat centered left and right, so there might be kind of a balance of masses. Although that's small, the 6 is quite a lot of mass on that right-hand side. So it seems about right. I mean, if my x bar, y bar is out here, then we know we made a serious error, right? So there's a decent eyeball check as the last thing to do on these kinds of problems. Any questions with you so far? Okay, our goal next is we're going to extend these formulas. We're really still going to use them in the next cases. So knowing what the meaning, the physical interpretation of the moment of the system about the y-axis or its tendency to rotate about the y-axis will be carried over into the continuous case. The only difference is the summation symbol must be replaced with an integral sign because we're going to take a limit of a particular Riemann sum. We'll leave Wednesday for that, since we have something like 2.5 minutes. Any questions so far, folks? Okay, this ought to be a good stopping point. Next class, we'll look at how to find center mass for regions like the one above.